Hey guys, Mr. Smith here, and in this video lesson slash mini lesson, we are reviewing or possibly previewing, maybe it'll be new to you, a little bit of an algebraic skill called rationalizing. So let's get started. So rationalizing, we do this in the context of when we have a rational expression and we have a denominator that's not an integer. So something like, you guys don't need to copy this down. Something like, let's say we had 1 over root 2, which is an expression that might have come up when you guys learned about trig ratios in your grade 11 course. Now, 1 over root 2, the thing about this expression here is, it's like, I know what 1 over 2 means. It means a half, right? I'm taking something and I'm dividing it by 2. What does 1 over root 2 mean? What does it mean to divide something into root 2? It's kind of weird. And so we have a convention in mathematics where we like to use denominators that are rational, not a square root. So this is in this lesson, we'll learn a few algebraic tricks to go from a denominator that's not, that it's a radical, to one where it's an integer. So the key idea is that we're going to be doing is we're going to be multiplying our expression by something appropriate that's going to clear the denominators. And again, generally we like to clear we like to rationalize denominators whenever we can. It's just a convention that that we use in mathematics. So when the denominator is a monomial meaning single term, the basic strategy we use is to apply the fact that, if I have a square root, say it's like the root of x. If I multiply that by another root x, then I get the root of x squared, or I just get x. And of course, this works when x is positive or 0. This wouldn't work for negative numbers because you can't root a negative number. This makes sense, right? I mean, like the root of x times the root of x would be x. Just kind of like the nature of how square roots work, right? It's like whatever the square root of 5 is, if I multiply that by the square root of 5, I'm going to get 5. That's the idea that we are using here. And we're going to make use of that to rationalize some denominators. Let's just dive in and see what that looks like. So here we have, let's look at A. Here we have an expression 3 over root 2. Nothing inherently wrong with this expression. However, the denominator is a radical. It might be nice if it wasn't. So what we do is we multiply by an appropriate value. It's grass cutting day, evidently. We're just going to roll with it. We're going to multiply by 1. So we don't change the expression, but specifically we're going to multiply by root 2 over itself, root 2. So think about it. Root 2 over root 2 is just equal to 1. We're not inherently changing this number because we're multiplying by 1. But look what happens. On top, 3 times root 2, well, that's just 3 root 2. On the bottom, root 2 times the root of 2, that's just equal to 2. So I might just make an aside there. Some of you guys, what I might do for this one, yeah, I'll just make a little aside. The root of 2, I didn't show this extra step here. Times the root of 2, just what you guys learned last year is that you can multiply the two radicands, the things underneath the square root, together. And of course, the root of 4 is just 2. I just went right there and got 2. All right, and so, you could argue, well, Mr. Smith, 3 over root 2 compared to 3 root 2 over 2, I find the first one simpler. That's okay. Both of those are perfectly fine. However, the second one has a denominator that is an integer. It's not a radical, and so this is just the preferred simplified version. And if you want to try on your calculator, just whip it out. 3 divided by the root of 2, and then do 3 times the root of 2 divided by 2, you're going to see that it gives you the same answer. They're equivalent. All right, Let's look at b, and maybe you can start to think to yourself, what can I multiply this expression by to clear to rationalize the denominator? So if you want to pause the video and think about that, you can, or if you just want to follow with me, that's fine too. The issue with the denominator is that we have root 10. The 3 is not a problem. So I'm going to multiply by, I guess I'm going to stick with green for the moment, root 10 over root 10. I don't need to multiply by 3 root 10 over 3 root 10. I can, and that's not wrong, but I'll just have some extra simplifying in the end. So what do we get here? 5 root 5 times root 10. So root 5 times root 50, using skills from last year. Sorry, root 5 times root 10 is root 50. And on the bottom, 3 root 10 times the root of 10. The root of 10 times the root of 10 is 10. So cleaning this up a little bit, we have 5 root 50 all over 30, which is correct. However, there's several ways we can simplify this. So this is just good review. So first of all, 5 over 30, we know that reduces to 1 over 6. Root of 50 can also be simplified too. So you guys did a lot of work in your grade 11 course simplifying radicals. We think to ourselves, is there a perfect square number that goes into 50? There is. 25 is the biggest perfect square number that goes into 50. I can write 50 as 25 times 2 inside that radical, all over 30. And now I'm going to do some simplifying here. So 5 over 30, that corresponds to 1 over 6, right? The root of 25 is 5. We're left with root 2. And then over 6. So 5 root 5 over 3 root 10. We have rationalized the denominator. It's equivalent to 5 root 2 over 6, which arguably is a bit more simple. And here we have a denominator that is a whole number. We also reviewed the one idea from your grade 11 math course, which was this property. And we're going to use this a few times today. The root of a times b is equal to the root of a times the root of b. We made use of that fact as well. All right, let's try the next one. See if it has as much simplifying. So we look at that guy. I think I'll stick to green for just showing this step here. We got a root 13 in the bottom. On the denominator, we don't want that. So we're going to multiply by root 13 over root 13. On the bottom, pretty simple. Root 13 times root 13, that's just 13. On the top, we got to use the distributive law. So we're going to have 3 times root 13. And then minus root 2 times root 13. That's the root of 26. And that's that. Now we think to ourselves, is there any way we can simplify this guy? On top, root 13 is a prime number. Can't simplify that. 26, there's no perfect square number that goes into 26. That's actually as simplified as we can go. So we're done that guy. But guys, the big idea from each of these guys, as you can see, is if the denominator is a monomial, it's like root 2, or it has like 3 root 10 or root 13. Just multiply by whatever that radical is. That'll clear out the radicals in the bottom. All right, so 3 examples under our belts. Let's continue. One more, however, look at this one. In this one, we have negative 4 plus root 3 over root 18. We could just proceed as usual. We could multiply by root 18 over root 18. However, it is good practice keeping things as small as possible. You might want to simplify if you can. Root 18 can be simplified. So I might just go, I have some space on my screen right to left here. I might just simplify the bottom this way. I'll show an intermediate step. 18, I can write as 9 times 2. And the root of 9 is just 3. So this simplifies to minus 4 plus the root of 3 all over 3 times root 2. And now that root 18 is simplified, I can now see that, okay, I don't have to multiply by root 18 over root 18. I can multiply by root 2 over root 2 using the same ideas as our previous three examples. On the bottom, let's do the top first, I guess. So we're using the distributive law. So what do we get? We get minus 4 times root 2, which can't be simplified. We get root 3 times root 2, which is root 6. That cannot be simplified. On the bottom, we get 3, and then root 2 times root 2 is 2. And I can simplify that. Negative 4 root 2 on top, plus root 6 all over 3 times 2 is 6. And there we go. And again, arguably, you might say, I don't find that any more simple, Mr. Smith. Okay, but now the bottom is an integer, and generally a little bit easier to, if these are rational, if we had another rational expression to add with that, generally easier to work with denominators that are integers. Again, it's just a convention we use. All right, let's continue. What if the bottom is not a monomial, it's a binomial? In this case, we do things a bit differently. And the way we do it involves the conjugate of a binomial. Now, if you've never seen a conjugate before, the conjugate of a binomial is just the same binomial, you just change the sign. So here we're multiplying. You can see what happens when we multiply conjugates. The conjugate of root 5 plus 1 is root 5 minus 1. These two guys are conjugates. It's the same binomial, just with a different sign. Same with the next guys, root 3 minus root 5 and root 3 plus root 5. They are conjugates. What happens when you multiply conjugates together? Let's apply the double distributive law to do this one. So root 5 times root 5 and root 5 times minus 1. Well, root 5 times root 5 is just 5. Root 5 times minus 1 is minus root 5. And then we'll do 1 times root 5 and 1 times minus 1. So we get plus root 5 and minus 1. But look what happens, guys. Negative root 5 and positive root 5 add to 0. And 5 minus 1 is just 4. What happens is when you multiply by that conjugate, you get no more radicals, which is pretty cool. You can see the same thing happens in part 2 here. Let's give it a try. So root 3 times root 3 is 3. And then root 3 times root 5 is root 15. Minus root 5 times root 3 is minus root 15. And then minus negative root 5 times root 5 gives you negative 5. And look, plus root 15 minus root 15, 3 minus 5 is negative 2. So this neat thing happens where you get rid of these radicals by multiplying by a conjugate, and it's guaranteed to happen. If you're not convinced, we'll do a few more. So we're going to use this strategy of multiplying by a conjugate in the following. So here we go. So what we basically used here, guys, is this idea of the difference of squares pattern, right? From your grade 10 math course. A minus b times a plus b is equal to a squared minus b squared. That's a special pattern, difference of squares, that you guys learned in your grade 10 course. And that hopefully, ideally, we have now in our math toolbox. But that's the basic idea. That's why it works. All right, let's continue. Let's clear some radicals out of the denominator in these two examples. So here we have 2 over 5 minus root 2. What we're going to do, guys, is multiply. I think I'll stick with my habit of using a different color. So we're going to multiply by 1, but in this form, 5 plus root 2, the conjugate, over 5 plus root 2. And then we just clean things up. So on top, we have 2 times 5, 10. 2 times root 2, so plus 2 root 2. Now, if you do more and more of these, you might get comfortable shaving off some steps. I'm going to show all 4 multiplications. But it means we get 5 times 5, 25. 5 times root 2, 5 root 2. Minus 2 times 5, minus 5 root 2, and then minus root 2 times root 2 minus 2. Now, as you do more and more, you'll understand, okay, the middle two terms always cancel out, and you might be able to save some steps. But here it wasn't too onerous for us. So we get 10 plus 2 root 2. And 25 minus 2 is 23. No more radicals. Integer on the bottom. Life is good. I want to say too, I mentioned in the first example we did, but you can, check your work anytime of any of these guys just by slamming them into your calculator. What is 2 divided by 5 minus root 2? And what is 10 plus root 2 root 2 divided by 23? You should get the same value. All right, let's try a couple more. If you feel like you're kind of getting the idea, I'd encourage you to just turn me off, turn me on pause, and try the next two, and then just fast forward and check your answers. That would be a reasonable thing to do. So we're multiplying by the conjugate, which would be 3 minus 4 root 3 over 3 minus 4 root 3. And then just clean things up. So on top, we get 3 times root 5. And then minus 4 root 5 times root 3 is root 15. On the bottom, I'm going to show all 4. Feel free to skip that step if you want, but we get 9. 3, so we'll get 3 times negative 4 root 3, we're going to have minus 12 root 3. And we'll have 4 root 3 times 3, that's plus 12 root 3. They always cancel. And then 4 root 3 times negative 4 root 3. So 4 times negative 4, negative 16. Root 3 times 3 is positive 3. If you can get to 48 in one step, good for you. I just did it in a couple there. These guys always cancel. And what are we left with? 3 root 5 minus 4 root 15 all over. You could do 9. I'll just show this step. Like, why not? You can, if you want to not copy, if you just want to go right to your answer, go for it. 16 times 3 is 48. And ultimately, we wind up with this 3 root 5 minus 4 root 15 over negative 39. Now, some people don't prefer negatives in their denominator. There's nothing inherently wrong with it, but it is often a common practice to rewrite with a positive denominator. So if we multiply the top and bottom of this expression by negative 1, this changes the signs around. We'd get 4 root 15 minus 3 root 5 all over 39. So that's kind of generally more accepted. All right, guys, one more. Let's give it a try. Again, feel free, if you got the idea, just go for it. Branch off on your own. If you want to follow along with me, please do that. But we're going to be careful. We're going to multiply by the conjugate of the denominator. So we're going to multiply by 6 minus root 2 over 6 minus root 2. And then clean things up. What do we get on top? 6 times 6, 36. 6 times negative root 2, negative 6 root 2. Negative root 2 times 6, another minus 6 root 2. And then minus root 2 times root 2 is positive 2. All right. And on the bottom, it's very similar, right? 6 times 6, 36. But just be careful. So 6 times negative root 2. So negative 6 root 2. But then we have root 2 times positive 6 plus 6 root 2. And then root 2 times root 2 is 2 plus minus, that's minus 2. It's on the bottom here when you're multiplying by the conjugate. Those radical terms cancel off. It doesn't work on the top here. So what are we left with here? We get, so 36 plus 2 on top is 38. Minus 6 root 2 minus 6 root 2. Those are like terms. Minus 12 root 2. And then 36 minus 2 over 34. So my previous answer bleeding in here a little bit. So that's okay. That answer is totally fine. However, we can simplify a little bit. Every single term there can be divided by 2. 38 divided by 2 is 19. 12 divided by 2 is 6. 34 divided by 2 is 17. So 38 minus 12 root 2 over 34 is totally correct. However, if this was from a resource like a textbook, in the back, they'd always have things simplified as much as possible. All right, so 3 examples of multiplying a binomial by a conjugate to rationalize the denominator. So at this point, we have previewed the skills we need and reviewed skills we need from earlier grades. We're ready to go, guys. We're ready to dive into some new content. Our first unit of this course will be on polynomial functions, and we'll get into that in the next video lesson. Until then, hope you guys are staying well. Have a great day, and we'll see you soon.